Welcome back. We continue with finite element for bar virtual work method. Virtual work, sorry. So virtual work is a method to find the stiffness matrix for bar. Okay, we consider one bar here. Okay, we consider one bar. This is bar. This is bar. The loading at the end is F1, and at this end we have F2. And we have a member load W. The position of W is L1. This is the length from W to end of this bar. So this is L1, and the other here the length from W to other end is L2. So we need to learn basic first before we find the stiffness K QF for uniaxial element. So we are going to use virtual work method later. Okay, so this is we consider first the real system. So after we apply the load F1 and F2, the bar will displace at U1 here at this end. So and other end it displays U2. And at X position, somewhere here, X position, so it displays U of X. So all this displacement, this is real. Okay, so U1 is real and U2 is also real. As we learned from last class or previous class, we need to approximate the function of Ux first. Okay, so the Ux comes from last class, and this is the simplest equation to represent the displacement Ux, and it is linear. So we assume that Ux is A0 plus A1x. So this is just a linear function. Okay, so if we plot graph, if this point, the displacement is U1, and at other point or other end point, here we have U2, so this is U2 displacement, and at other place Ux, so this is Ux, and we can connect U1 and U2 by a linear line, because we assume that Ux is A0 plus A1x. So this is just a linear function. Okay, so we go to next slide. We need to approximate A0 and A1. A0 and A1. Okay, so this is linear function. We assume that here the position here is x equal to 0. The element length is L. So here at this end x equal to L. Okay, so we still use Ux is a function of this A0 plus A1x. So we impose the boundary condition. So at U0 here, U0, 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 at U0, U equal to U1. So this is U0. At U0, this is equal to U1. So we use this function. So this is U0. So U0 is A0, A0 plus A1 times A1 times X. So X at endpoint here, X is equal to 0. So this is equal to U1. So we found that A0 equal to U1. At other end, at this end, U of L equal to U2. U2. Recall back this equation. So we substitute S equal to L here. So UL equal to A0 plus A1 times X. X is equal to L now. So A1 times L. So equal to U2. Okay, from here we found A1 equal to this. So this is A0. We substitute to this U1. So A0 is equal to U1. U1 plus A1L equal to U2. So from here, after we solve, we found that A1 equal to U2 minus U1 per L. Okay, so we substitute back the parameter A0 and A1 here. We substitute back to this equation. So this is A0 and A1 equal to this. We substitute back here. Okay, A1. So we found this. So this is A0, U1. So U1 plus A1 is this. So this is A1 times X. We simplify this and we factor. So this is first factor for U1 and this is second factor for U2. Okay, so from last class, this is U1 and U2 represent the nodal displacement, and this is we call shape function. So this is N1 of X, and this is this term is N2 of X. This is called shape function. We introduce N1 is equal to this, N2 equal to this. Okay, so we go to next slide. This is from previous slide. Okay, so this term from previous or last slide, this term we call N1 of X multiplied to U1. So multiplied to U1 plus N2. So this term we call N2. So N2 of X times U2. We can use matrix multiplication. So this is n1 times u1. So this plus n2 times u2. So this is we call row vector. Okay, and this is we call column vector. So denote that as n. N, this is row vector of 1 times 2, and this is u. We denote it as u. This is a row vector, so this is 2 times 1. So ux is equal to nu, shape function times nodal displacement. We can change position here. This is n1. We can put it here. This is a row vector. We can also this is come first and come first and u come second. So we can put this come second and u come first. Okay, come first because so if we see from here n1 times u1 equal to u1 times n1, and plus n2 times u2 equal to u2 times n2. So we can change a position. This is first position, and this is second position. So if we change the position so that it come first for u, so we need to change. This is column vector. We need to change to row vector. And similarly this. So this is row vector, which is comes from first term, and we can move to a second term, but it will change from row vector to column vector. So this is u. We use this symbol to represent the row vector. So multiply to n. So this symbol is a row vector. So un and is equal to nu, but we change either the row become column vector or the column vector change to row vector. Okay, so in the next slide, we will consider the bar element again. Determine the strain displacement relation given ux, determine strain x. So this is bar element. It displays u1 at this end, and other end it displays u2. We consider one small element of distance delta x, where x is the length, x is the position of this side. So this is x, and this is x. So this is the position. The position here is x, and the position here is x plus delta x. At this side, from last slide or previous slide, the u, the displacement u, is a function of position. Okay, so this is position is x at this side, so it will displace of u of x. okay, u of x. And at this side, the position is x plus delta x. So it will displace to u of position. So position is x plus delta x. Okay, so this element, this is original one before deform. So after deform, it go to ux, yeah, ux, u of x. Okay, and this side, because the position is u x plus u of x plus delta x, so it will go to this. Okay, so this side go to here. So the length here is, or the displacement here is u of x plus delta x, or u of position. Okay, so from a basic definition of strain. So this is strain. Strain is in x direction is equal to final length minus original length. Original length per original length. Okay, original length. So this is basic definition of string. So from here, this is original length. This is original length delta x, and this is final length. Okay, we need to find the final length now. So the final length is this. The final length is delta x. We take this is as this point as origin. So this length is delta x. This element is delta x. So this is delta x. So plus ux plus delta x. Ux plus delta x. So all this is the distance from this this is the distance from this point to this. Okay, so this from to this, this is the length. So to get the length here of this space element here, so this length we need to minus to this length. Okay, so this length is ux. So this is ux. So we need to minus to ux. So all this term now is a final length of this element. So final length of this element, we need to minus to original length. So original length is delta x. So comes from this. This is original or delta x, original length. So final length minus original length per original length delta x. So this is definition of strain. Okay, after we simplify this, so this is cancel. So this is remain this. Ux plus delta x comes from here minus ux this. So per delta x. So all this represent the string. From basic calculus. From basic calculus, if we take the limit here, so this is ux plus delta x minus ux per delta x, and we take the limit so that delta x approach to 0. Okay, so this term is definition of du per dx. Okay, if we consider back to a secondary school, so if we have this is graph y and this is graph x, this is x-axis, so we have a graph here. So this position is x, so this is y of x. We consider a limit. Okay, so this is x, this is delta x. Okay, delta x. So this is y, and this is also y. So this is from secondary school. This is delta y. So if we take this is x, y is y of x. The position here is x plus delta x. So this length, all this is y of x plus delta x. Okay, from calculus dy per dx, is delta limit delta y per delta x. So this is delta x approach to 0, and this is delta y is this. So delta y is y x plus delta x plus delta x just now, yeah, minus y x this distance minus this distance. So this is delta y. So minus y x, okay, per delta x. Okay, so this is definition of dy per dx. So yx plus delta x minus yx per delta x is dy per dx. So this is look like same, yeah. Okay, this is look like same. So y we replace with u. So this is y x plus delta x. So this is u x plus delta x minus ux replace y, and this is still per delta x. So all this term, if we take limit delta x equal to or approach to 0, so we will get this is string now is equal to du per dx. Okay, du per dx, and we use this symbol also for to represent du per dx. So this is u prime of x. So this is du per dx. So du per dx now is straight. So we can conclude that strain is equal to du per dx, where u is a displacement function. Okay, from last slide, we found that strain is equal to du per dx. So we need to recall back Ux is Ux from last slide is N1 U1 plus N2 U2. So we need to substitute here for Ux. So this become derivative or d per dx. So once we substitute, we get this. So this is Ux. So this is N1, N2, U1, U2, or N1, U1 plus N2, U2, or this. So this is we substitute all this to here, Ux. And N1 and N2 are the function of x. This is the function of x. And this is not function of x. So this is U1 and U2 all are nodal displacement. So d per dx of N1 of x is this N1 prime x, and d per dx for this term is N2 prime x. So this is keep maintain U1 and U2. We can simplify all this term. This is a row vector. So this is a row vector. So we simplify as N prime x. And U1, U2, as usual, we use or we denote it as U vector. But N1, this term is d per dx of N1. So N1 is from last slide, N1 is this. So this is N1. So we found that from previous slide, N1 is 1 minus x per L. So N1 prime, so this is differentiate of N1. So this is differentiate d per dx. We need to differentiate N1. So N1 is 1 minus x per L. So from here, we get minus 1 per L. And N2, this term, we need to consider this term now. So this is N2 prime x or differentiate of N2. So this is differentiate of N2. So difference N2 comes from last slide. So this is N2. So this is N2 just now. So N2 is x per L. So we need to differentiate N2. So this is x per L. Once we differentiate, we get 1 per L. So this term we can substitute to here. This is N1 prime x and N2 prime x is equal to 1 per L. So we need to substitute to here. So we can get this. So from here, we found that strain X for bar element or two bar element, with two nodes, So we found that the strain here is this minus 1 per L, 1 per L, U1, U2. We consider two node bar element, and we found that this function, all this function is not depend on X. So strain X just now is differentiate of N1 and N2. So suppose this is a function of X. But here, if we consider two node bar element, the X term is lost. So we found that this is no more X function. So we can conclude that the strain X for bar element at any point here, we found that the strain is a constant. So this is constant. Okay. So we go to next slide. The strain is this. This term we call B matrix. So this term we call B matrix. This is famous in finite element method. The differentiate of shape function we call B. Okay, and this is U1, U2. This is nodal displacement, so we denote it as U. So strain equal to BU, where B is this differentiate of shape function. So from previous slide, this is this. Okay, so as now strain from this, we can conclude that the strain is related to nodal displacement U by B, the factor B. Next, we need to consider stress. Okay, stress for bar element. So this is bar element. We need to consider stress also. So this is stress X. And the allocation of this element in the bar, we need to relate to strain just now. So stress from definition, usual definition, stress X is E times strain for elastic material. So this is stress, this is strain. So this is straight line or linear relationship between stress and strain. So the slope is E. So stress is equal to E times strain X. So this is equal to E. So strain X just now is equal to BU. So we substitute strain equal to BU to here, to strain. So this is become BU. And if we replace term E by D, so this is become dB dBu. So this is famous also in finite element method. This is material matrix D. Okay, so stress is equal to dBu. For other for 2D, 3D problem, we need to replace with D. So D is a matrix for 2D and 3D problem. But for 1D problem, D is equal to E. Now we go to next slide. We consider equilibrium equation. Equilibrium equation. We need to find, if we refer back to stiffness method, we have, or we, this is, okay, in the stiffness method, we have Q equal to K, where K prime is equal to local stiffness matrix, and U represent the local U or local displacement. This is local force. This is basic stiffness method before. So we need to find K prime. How to find K prime? Okay, so in finite element method, we have many methods. Once we need to consider equilibrium equation, and we have many more methods to find K prime. Because before we consider K prime, we consider first equilibrium equation. So this is an element inside, maybe inside in the bar element. So we just have only one direction stress, sigma x. Okay, the element is dx, dz, and dy in length. So here at this phase, we have sigma x or stress x. So at this phase, we have stress x plus increment term. So increment term is d sigma x. So if we apply the equilibrium equation, total Fx equal to 0. So we just consider only one equation only because this is bar element or one direction stress only. Okay, so from this is stress x. So we can create a force now. So stress x times the area of this phase is equal to force. So stress x multiplied to area of this is dy times dz. So dy times dz. So this is force. We take minus here because the direction is to negative x. Okay, so to maintain equilibrium, so we need to consider one more. We need to consider this force. So this is stress x plus d sigma x, and this is stress. So we need to multiply to this area to get force. So this area is dz times dy or dy times dz. So this is dy times dz. So for equilibrium, we need to equate to 0. And then after we simplify this, we have a few terms will vanish. So the remaining term is d sigma x dy dz equal to 0. Because dy per dz is not equal to 0, is non-zero, so 0 per non-zero or 0 per dy per dx is dz, 0 per dy dz. Of course, we will get 0. So we found that this d sigma x equal to 0. Or d sigma x per dx equal to 0. Okay, so we go here to here. So d sigma x dx equal to d per dx, and sigma x from previous slide, sigma x is equal to e times strain. So this is equal to 0. Okay, so d per dx, this term, e, this, and strain x from last or previous slide, strain x we define as du per dx just now. So we substitute strain term here. Strain is equal to du per dx. So we get this. So e du per dx equal to 0. Okay, e is just a constant, not depend on x. We can move out from differentiate d per dx. So it appear here. So e, and this is d du per dx. D per dx, du per dx is equal to second differentiate. Okay, d we differentiate 2 times u. So this is du per dx. So this is a differentiate of u with a second or 2 times differentiation. Okay, so second or second derivative or 2 derivative of u. We need to differentiate 2 times. So this is equal to 0. So we found this. So this is equation. So e a differentiate of u 2 times equal to 0. So this will form an equation. So this is an equation. So this is also, we call it as differential equation. We have one course in civil engineering program. We have one course differential equation. That's why we need, this is important in engineering, all engineering program. The differential equation is quite important because in engineering problem we have many equation or differential equation. So this is fundamental in finite element method. We need to solve differential equation. So basically in finite element method, we need to solve differential equation. Okay, so I think that's all this lecture. See you later. Assalamualaikum and have a nice day. Goodbye.